So our next speaker is Zoi Rapti from the University of Illinois at Urbana-Champaign. She'll be speaking about her C3.ai DTI research project that is titled Spatial Modeling of COVID-19, Optimizing PDE and Metapopulation Models for Prediction and Spread Mitigation.
I will talk about some recent progress that we have made. It is indeed our project about spatial modeling, and we're interested in data, both mobility data, but also epidemiological, of course. So spatial modeling, and we're interested in human mobility. So human mobility plays an indisputable role in the spread of COVID-19, as previous studies have shown. For example, there was a science study that showed that travel restrictions initially, when the pandemic started, they decreased the case importations by a huge amount, almost 80%. That was like a global study. So they considered mostly air travel. There are other studies that are more localized in nature, but still spatial. For example, many have studied commuting and its role in spreading the disease. One such example is the Arenas paper from 2020. This one focuses on commuting in Spain, which is important for us too, because the example that I will talk about today has to do with the autonomous community of Andalusia in Spain. So that study was used to study the effect of mitigation measures, such as decreased mobility, and study how the reproductive number of the disease varies over time. Another study, also from 2020, considered intercity mobility data. It's great to use those when they are available. And they studied the proportion of asymptomatic infectious people who traveled over that initial period of the pandemic. And they found that almost 86% of the infections, they were caused by asymptomatic people, which is really striking. There are also more mathematical studies, like the one by Berestiki, that has recently appeared in the bulletin of MathBio. And what they did there is they used a PDE model, a reaction diffusion model, to study the role of highways. The motivation was Italy, because it was shown in previous studies that a lot of new infections, they appeared along the highway network of Italy. So what we're doing is we are using one type of data, which is link flow measurements from Andalusia's transportation network. These data are readily available on the website of the government of Andalusia. I wouldn't say exactly readily because Ria Kondu, who is also the PI on this grant, had to work very hard in order to make this work. So it's a non-trivial enterprise to obtain origin destination matrices between different locations. So as a beginning of this project, what we did is we studied a metapopulation model for 8 provinces. And like I said, there are sparse data that exist along the highway of the highway network of Andalusia. So Ria and her collaborators, they created the most likely origin destination matrix obtained from those data. And they did so by applying entropy maximization principles. So let's see what's known and what's unknown that needs to be found. So the available data are link volume, namely how many cars pass a certain point along a link. And we assume that we have a network of n nodes and m links. Here it's just 8 nodes and 13 links. That's what I'm showing here. It's an oversimplified version of the actual network. And the objective now is to populate the trip matrix entries that tell us how many trips start at origin I and end at destination J. So we need to find the proportion of trips with origin I and destination J that go through link A. As an example, you can go from Seville to Cordoba directly, or if for some reason you have to go through Granada and Cordova, and then Cordova. So this is what the type of, what I mean when I say the proportion of trips. And again, this is an oversimplified version. I'll show you the actual map in a while, and you will see what the challenges are. So we know that the sum of all trips, they have to be preserved along a link. And that's what we're showing in this equation here. And so what the method of entropy maximization is, if T is the total number of trips, then all the possible number of ways to construct the matrix is given by this formula here. And what we are trying to do is we are trying to maximize this S here, the end that we call the entropy, based on the constraint star. So the idea is that the higher the entropy, the more information content we preserve from the observed traffic counts. Now, this method is supposed to be superior to other methods. The advantages are that there are no parameters to be fitted, like for example in a gravity model. And also, most importantly for us, we can account for time fluctuations in the number of trips. And that's important because Spain had several phases over this epidemic. So there was the before, during, and after lockdown phases that we're interested in. And this method allows us to account for these changes in mobility. The other models, they're kind of static because they depend on the population of the origin and the target location. So that's why we think that this origin destination matrix approach based on entropy maximization is probably, it fits better our project. So there are some challenges though. So Andalusia's traffic map reports, as you can see here, it reports several such measurements. There are all sorts of link flow stations, permanent, semi-permanent, and others. So, so we had to do a lot of checks to select the appropriate volume label input. So fortunately, that all has been done now. So that's the first step of the project. Since this is a metapopulation model, that takes care of the links, how we're linking our metapopulations. The next step is, of course, to define the model for each node. I show here a cartoon of the single node model that we're using. We have susceptibles, they move into the exposed class after contact with either asymptomatically infectious host or symptomatically infectious hosts. And then they progress to the corresponding compartments. Asymptomatic hosts, they go into what we call the U class. This is the underreported recovered. The infected ones, the ones that are being recorded by the authorities, they move into the recorded class, or unfortunately, we know that COVID can be fatal, I mean, the disease. So this is the compartment that takes, that accounts for the fatalities. So these, the equations, if you're interested, can be shown here. The MIJs are taken from the previous part that I talked about, the mobility part of the project. Here we make several assumptions. One is that, of course, we care about the proportion of asymptomatic in the living population. That's why we subtract here the dead, the diseased hosts. Similarly, when people travel, usually it's not those who are infected and reported infected with symptoms, and neither the diseased, so we subtract those two. This theta here accounts for vehicle occupancy, and it varies. It can be 1.5 to 2 usually. That's what several studies show. And we have several parameters here that are unknown. So phi is the fraction of the exposed that become asymptomatically infectious. 1 minus phi is those who are symptomatically infectious. Sigma alpha is the average time, the inverse of the average time it takes to go from the E to the A class. And sigma I has a several similar meaning here. Gamma alpha is the inverse of the recovery period for the asymptomatically infectious, gamma I for the symptomatically infectious. Chi is the inverse of the average time to death, and omega is the fraction of those who are recorded as infectious. What's the fatality fraction? So for this relatively simple model, we have 7 parameters. We assume that gamma alpha is well known, so that's the only one we fix. So we're left with 6, and you can see here what the single node R naught is. So there's a contribution from the asymptomatically infectious and one from the symptomatically infectious. This kappa alpha over kappa A plus kappa I, these are the fraction, if you like, of the asymptomatically infectious, and kappa I over kappa A plus kappa I is the fraction of the symptomatically infectious. I need to point out here that it's impossible from this model to learn, and the data, to learn what phi and omega is separately. So what we do is we lump together, and the parameters that we optimize are kappa A, kappa I, kappa R, kappa D, and the 2 betas. And next, here are some results from our optimization. From the optimization part. So we are using daily confirmed incidence of cases, especially for the first phase of the epidemic. There wasn't that many fatalities back then. And this is before the announced the first stage of the mitigation measures. But we are going to incorporate fatality incidents later, in later phases. And of course, we don't have to stick with the province level and consider 8 provinces. We can go at lower administrative divisions if we want to achieve a finer scale of this. And here I'm also showing some results from our regarding R naught. What we see here echoes what other people before me have talked about today, namely that asymptomatic, the contribution of asymptomatic infectious to disease spread is considerable. And so what we do is we show the R naught for the 3, just for this example, just of 3 of the 8 provinces. And you can see how much larger the contribution from the asymptomatic is compared to the symptomatic. Of course, what we did next is to find the metapopulation R naught. This is obtained as the spectral radius of the matrix F times V inverse. So here, for a general metapopulation with n nodes, what F does is it describes the inflow of new individuals into the infected infectious classes. So this is what's coming in. So you can see that we only get non-zero matrices along the diagonal. And that's due to the new infections. And V now describes all the other flows that take place within our system. For example, when asymptomatically infectious hosts, they move from one province to the other, this is not considered a new infection. It's just population moving from one compartment to the other. And this is what's happening in these VII matrices and VIJ. So one of the, it's the formula for R naught, the metapopulation R naught is unfortunately quite ugly to show. But one of the things that we found is that when mobility is low, then the metapopulation R naught can be approximated to a good degree by the largest R naught among the nodes. And that makes also heuristic sense. If you look at here at these formulas, basically what I'm saying is that when the MIJs, MJIs are low, then these parts can be ignored. And what you get is basically a diagonal matrix here. And when you find the inverse and multiply with F, you get just as R naught, you get the maximum of the R naughts of the various provinces or various nodes. So what are the next steps of this? So we plan to apply this method at a finer scale, probably at the municipality level. Such data exist. Also, we plan to obtain data and results for other regions, not just Andalusia, Spain. And finally, over the summer months, Spain and Andalusia had a large influx of tourists. This cannot be considered as movements within the community. So that's why we plan to incorporate population influx from external locations. And I'm just showing here another result from the model where we consider not only the first phase, but also the second phase after the first light measures were introduced. So with that, I can stop here. Thank you.